In previous example, we talked about resonance structures. So take a minute to pause this video and draw the possible resonance structures for CNS minus thiocyanate ion. So these are the possible resonance structures for thiocyanate ion. So thiocyanate ion has three resonance structures. Let's say this is A, this is B, and this is C. As I explained in the previous video, I explained that each resonance structure contributes to something called the resonance hybrid. Okay, so one may contribute more than the other, while they may all contribute equally. But if you look at this now, look at the difference in the structure. You realize that each of them will contribute differently to the resonance hybrid. Okay, and if you want to take a guess, how do you think the resonance hybrid will look like? Okay, take a pause this video and draw the resonance hybrid from these three resonance structures. Okay, so this here is the resonance hybrid. So these three resonance structures. Okay, resonance structures, they are contributing to the resonance hybrid, but one of them may contribute more than the other. Okay, so how can we know the one that contributes more than the other? We have to calculate something called the formal charge. The formal charge is like an hypothetic charge assigned to atoms in a molecule. Okay, like an hypothetic charge that is assigned to each atom in a molecule, and it determines or tells us which resonance structure is contributing mostly to the resonance hybrid. Are you getting that? And the formula for formal charge, let me write it up here. Formal charge is equal to the number of free valence electrons in an atom minus the number of allocated allocated valence electrons. Allocated, I mean the one that belongs to that particular atom. And the number of allocated valence electrons can be defined by two things. One, for you to get number of allocated valence electrons, it is the number of lone pairs of electrons around that particular atom plus half number of shared electrons. For example, if you look at this bond over here, there are two electrons in this bond, right? There are two electrons here. So half of it belongs to this sulfur and half of it belongs to this carbon. That means in this bond you see over here, one electron belongs to carbon and one electron belongs to what? To sulfur. In this bond in green up here, there are two electrons here. One belongs to carbon, one belongs to nitrogen. In this one in white, in the middle bond in white, there are two electrons here. One belongs to carbon, one belongs to nitrogen, and same as the one the green below. That means how many electrons are allocated to carbon? One from this bond, one from this bond, one from this bond, and one from this bond. That is how many? That's four. That's how to calculate number of allocated valence electrons. Note something. The formal charge, as I said, is an hypothetic charge that is given to atoms in a molecule. So it does not belong to the entire molecule. Okay. So this charge you see up here, this minus you see up here, this is not formal charge. It is the atoms in the molecule that will have a formal charge. Are you getting that? Let's calculate the formal charge of each of the atoms in each resonance structure. Let's start with this sulfur. Okay. Formal charge says, the formula says what? It says the number of free valence electrons in sulfur. There are a total of six valence electrons, isn't it? Six. That's free. Free means the normal sulfur atom, there are six valence electrons, minus number of allocated means the number of lone pair plus half number of shared pair. How many lone pairs do I have? Let me color it in orange. We have one, we have two, and how many allocated do we have? Now look at these three bonds. Out of each bond, one electron belongs to sulfur and one belongs to what? Carbon. So let's count the one that belongs to sulfur. One here belongs to sulfur, one here belongs. Now we have two. Let me paint them in orange so it's very clear. So there are, for every bond there are two electrons in orange. So this one belongs to this sulfur, while this one here belongs to this carbon. So let's calculate the one that belongs to sulfur. Let's count one, two, three, 4, and 5. That is 6 minus 5. That will give me plus 1. The plus 1 is the formal charge of sulfur. For carbon, the formula says number of free valence electrons. In carbon, there are 4 valence electrons in carbon minus number of allocated. Allocated is lone pair plus half number of shared pair. But there's no lone pair on carbon, so let's count the number of shared pair. Half number of shared pair. So this one I explained earlier. This one belongs to carbon. This one belongs to carbon. This one belongs to carbon. This bond you see here, there are two electrons here as well. One belongs to what? One belongs to carbon. That is four allocated electrons. So when you subtract, you have 0. For nitrogen, the formula says number of free valence electrons again. Free valence electron in nitrogen is 5 minus the number of allocated. Let's count our electrons around nitrogen. We have 1, we have 2, we have 3, we have 4, we have 5, we have 6, and we have 7. So that is 5 minus 7. That will give me a formal charge of minus 2. I think you get the idea. So let's do that for the rest. You can pause the video again and try the rest. Okay, so this will be 6. That's free valence electron is 6 in sulfur minus allocated. Let's count. We have 1, 2, 3, 4, 5, 6, and 7. That will give me minus 1 from our charge. For carbon, there are 4 valence electron minus allocated valence electron. We have 1, 2, 3, 4. Just count what is around carbon. The electron around carbon, just count it. So that's allocated. So 4. That will give me formal charge of 0. For nitrogen, there are 5 valence electrons minus, let's count those around nitrogen here. We have 1, we have 2, we have 3, 4, and 5. So 5 minus 5 will give me 0. Okay. For this one over here, again we have 6 minus let's count 1, 2, 3, 4, 5, 6. That will give me 0 from our charge. For carbon, 4 minus, let's count again, 1, 1, 2, 3, 4. That will give me 0 from our charge. And for nitrogen, 5 minus, let's count, 1, 2, 3, 4, 5, 6. That will give me minus 1 from our charge. So I think you get the idea on how to calculate from our charge. So this things you see, these numbers you see here, they are called formal charge. Okay, so let's take a look at another example. Let's take a look at CO2. So again, can we draw the possible resonance structure? Or does CO2 show resonance? Let's see. So there are, first let's draw the level structure of CO2. So this is level structure for CO2. So you can see carbon does not have a stable octet. So that means that there can be different resonance here, can be different resonance structures rather. So carbon can take 2 lone pairs from the left oxygen atom to form 3 bonds here, so you can have a stable octet. You can take 2 lone pairs from here as well to form 3 bonds here, so you can form a stable octet. You can take 1 from here and 1 from here. It's also going to form a stable octet. Let me show you what I mean. So these are the possible resonance structures of CO2. Okay, so they are all contributing to the resonance hybrid, but one of them may contribute more than the other. Are you getting that? So that's where formal charge comes in play. As we said earlier, we said formal charge. Let's come back up here. It says that formal charge is the number of free valence electrons minus number of what allocated valence electrons. So let's do that now for each of the atoms. Okay, for this atom here, for this oxygen atom, there are 6 valence electrons in oxygen atom minus how many is around it? Let's count. Let me use a different color for that. So let me use a different color. We have 6 minus, let's count. We have 1, 2, 3, 4, 5. That should give me plus 1. For this carbon, we have 4. That's number of free valence electrons is 4 minus allocated around it 1, 2, 3, 4. That should give me 0. And for this, we have 6. That's 6 valence electrons minus around it 1, 2, 3, 4, 5, 6, 7. So that should give me minus 1. So let's do for the rest as well. We have 6 minus 1, 2, 3, 4, 5, 6, 7. That will give me minus 1. We have 4 minus 1, 2, 3, 4. That will give me 0. You know I'm getting this 6, this 4, and this 6 from? That's the number of valence electron in the free state of oxygen of the atoms. I getting that? So 6 minus how many electrons are around this oxygen? Let's count. 1, 2, 3, 4, 5. So that should give me plus 1. Same goes for this atom. We have 6 minus, let's count 1, 2, 3, 4, 5, 6. That should give me 0. Okay. For this one, we have 4 minus 1, 2, 3, 4. That should give me 0. And for this, we have 6 minus 1, 2, 3, 4, 5, 6. That should give me 0 as well. Now you might be asking yourself that what is the need of calculating this formal charge? I explained earlier that formal charge, calculating formal charge will help us know which resonance structure is contributing mostly to the resonance hybrid. Okay. Now there are two key factors you should note. The first one is the closer the formal charge of individual atom in a molecule is to 0, D, sorry, I meant to write D, the more it contributes to the resonance hybrid. The closer the values of the formal charge is to 0, the more that atom contributes to the resonance hybrid. Take for example, this was minus 5. This is very, very far from 0, right? So you can say that this structure does not contribute to the resonance hybrid. Do you understand? That's what it's all about. That's what I meant by this statement. So the closer it is to 0, the more it contributes to the resonance hybrid. And the second point is, one is a little bit long, so but it's quite explanatory. It says, in a resonance structure, if the more or less negative atom carries a negative charge, okay, that means that if a negative charge is present on a more or less negative atom, okay, that structure, that resonance structure, contribute mostly to the resonance hybrid. So if, take for example, we have two atoms, we have, let's say we have carbon and we have nitrogen. We know fully well that nitrogen is more or less negative than carbon, right? Uh-huh. So if a negative charge is found on nitrogen, because of negative charge is found on a more or less negative atom, the resonance structure that that negative charge is found in will what? Will contribute mostly to the resonance hybrid. That's the rule. Okay, so let's look at the first rule. The first rule says, again, the closer the formal charge is to 0, the more it contributes to the resonance hybrid. So let's take a look at this CO2 molecule. Okay, we're having, look at the formal charge, plus 1, 0, minus 1. They're close to 0, that's quite all right. Minus 1, 0, minus plus 1. They're also close to, they're like a tie. These two are like a tie. But look at this here. What do you see? 0, 0, 0. Because this is the closest to 0, it means that this structure, this resonance structure, will contribute mostly to the resonance hybrid. That's why when you look at the diagram or the structure for CO2, this is how we draw CO2. Why? Because this is it. This is the resonance structure that contribute mostly to the resonance hybrid. Let's take a look at the other example. The first one we did, 2 look at following the rules now. The one that is closest to 0, the one that has formal charge closest to 0 will contribute mostly. Look at the formal charge here. We have plus 1, we have 0, we have minus 1, we have minus 1, 0, 0, we have 0, 0, minus 1. These two, that's resonance structure B and C are like a tie because we're having 0, 0, minus 1, having 0, 0, minus 1. But look at resonance structure A, we're having minus 2. It's far from 0. So that means that this structure is out. So you are left with what? You are left with resonance structure B and resonance structure what? C. Now, since they are a tie, we go to second rule. Second rule says that the resonance, the one that is carrying negative charge, if the one that is carrying negative charge is more or less negative, isn't it? So let's look at this now. Which one is carrying negative charge? We have this here and we have this over here. You can see sulfur here is carrying a negative formal charge of minus 1, and nitrogen is carrying a formal charge of what? Of minus 1 as well. Now, in case you don't know, nitrogen is more electronegative than sulfur. The electronegativity of nitrogen is around 3.0, and the electronegativity of sulfur is around 2.5. Okay, So since nitrogen is more or less negative than sulfur, and nitrogen here is carrying information of -1, according to what this second rule says, that means that this resonance structure over here is contributing mostly to the resonant hybrid. So the most acceptable structure for thiocyanoate ion is this.